turn this a little bit this way. Okay, we are now ready to record. Today, we're going to be doing Advent of Code Day 17. This is basically a month-long challenge through December up until Christmas, where every day there's going to be 2 programming puzzles released. I'm going to be doing every single one of them and making video solutions. That's what this is all about. If you want to check out other videos from this series, make sure to check the playlist in the description. And yeah, we're just going to do Day 17 today. Oh yeah, also if you want to check out the code, it's going to be at a GitHub repository, which is linked down in the description. So make sure to check that out as well. And one more thing before we start, we are nearing 400 subscribers. So I would really appreciate it if you could support me and just, hit that subscribe button. It's free. You can always unsubscribe at any time. And according to YouTube statistics, only 11% of you are subscribed. Okay, no one cares. All right, so Day 17, Conway Cubes. As your flight slowly drifts through the sky, the elves at the Mythical Information Bureau at the North Pole contact you. They'd like some help debugging a malfunctioning experimental energy source aboard one of their super secret imaging satellites. The experimental energy source is based on cutting-edge technology, a set of Conway cubes contained in a pocket dimension. When you hear it's having problems, you can't help but agree to take a look. The pocket dimension contains an infinite 3-dimensional grid. At every integer 3-dimensional coordinate xyz, there exists a single cube which is either active or inactive. In the initial state of the pocket dimension, almost all cubes start inactive. The only exception to this is a small flat region of cubes, your puzzle input. The cubes in this region start in the specified active or inactive state. The energy source then proceeds to boot up by executing 6 cycles. Each cube only ever considers its neighbors, any of the 26 other cubes where any of their coordinates differ by at most 1. For example, given the cube at x equals 1, 2, 3, given the cube at coordinates 1, 2, 3, its neighbors include the cubes at 2, 2, 2, and the cubes at 0, 2, 3, and so on. During a cycle, all cubes simultaneously change their state according to the following rules. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube remains inactive. If a cube is inactive, but exactly 3 of its neighbors are active, then the cube becomes active. Otherwise, the cube remains inactive. So this is kind of like Conway's Game of Life, if you ever heard of that. I'll leave a link to that in the description. It's pretty well known. It's like a 2D simulation of this. Basically, yeah, kind of. The rules are a little bit different, but this is kind of like the gist of it, and it's in 2D. Okay, the engineers responsible for this experimental energy source would like you to simulate the pocket dimension and determine what the configuration of cubes should be at the end of the 6-cycle boot process. For example, consider the following initial state. And it gives an example. Even though the pocket dimension is 3-dimensional, this initial state represents a small 2-dimensional slice of it. So it's just a flat region. That's what the input describes. Simulating a few cycles from this initial state produces the following configurations. Okay, and then it just goes into this pattern. After the full 6-cycle boot process is complete, 112 cubes are left in the active state. Wait, 1 second, I'm just going to review this. Okay. Starting with your given initial configuration, simulate 6 cycles. How many cubes are left in the active state after the 6th cycle? Okay, so this problem shouldn't be too hard. The input's actually rather small. But yeah, we're just going to go about doing this, and yeah, I'll be back in about 5 seconds. Alright, so we have our answer. Our answer is 196. And I get a feeling that we did something wrong. Yeah, it's too low. So 196 is not the right answer. Okay, why don't we try this on the input? I'll be back soon, right? Okay, that was way too much time spent on this. But 195 is our answer instead of 196. No. 196 was too low. Okay, wait, no. Maybe we just need to increase how much space we need. So, okay, that's probably too big. 100 is too big. So, 1, 2, 3, 4, 5, 6. Okay, 215 is our answer. 32 seconds. Alright, this is going to be a tense 32 seconds. Okay, I'm going to try again. What was our answer? 215? 2 seconds left to wait. God. Oh my goodness. Okay, I need to explain this, but I have no time right now. I'll be back in about 2 hours, but Yeah, I'll just explain later. Yeah. All right, so we're back, and it's time to explain the solution. So I actually spent a lot of time debugging this because there was just some errors that I found wrong. First of all, if you were getting errors while you were trying to run this and you're coming here for, I guess, help, one major thing about this is if you're looking at the input's actually wrong. So don't look at this for help. I was really confused by that, and then I looked on the subreddit, and there were people saying that the input example was wrong, so that's incorrect. Don't necessarily look at that for help. But so let's just explain, I guess. So the overall strategy here is just to simulate it, right? It's pretty clear what we have to do. It's just not exactly clear how we're going to implement that. So how we're going to implement that is basically we're going to have a big matrix which represents our three-dimensional space. And in this example, I'm using a, let's see, 50 by 50 by 50 cube. I'm just taking that subsection of the infinite space and just using that to simulate our, I guess, what is it called? A computer or what? Experimental energy source pocket dimension. So this is our little slice of our pocket dimension. It's 50 by 50 by 50. And we just need to set this number to be big enough such that it can contain all the operations and nothing gets leaked out. But we can't have this be too big that our data can't run. I mean, like, our program won't terminate. So we need this to be small enough that our program will terminate. But we can't have it be so large that it's... we need it to be large enough to contain all the operations. Okay, so first... I had a useful function for debugging. I'll include that in the GitHub repository as well. And then we just have our main function. And this function basically just generates the next state based on our current state. And our state is going to be a 50 by 50 by 50 cube. So we basically just have these variables saying the min x, y, z. And our matrix, our big grid is going to be... Our cube, I guess, is going to be in 3 dimensions. So it's going to be a list inside a list inside a list. And if I print that out, actually I'm not going to print that out, but you can visualize what a list inside a list inside a list is. Basically, you just have a 2-dimensional grid, and then you have that repeated multiple times. I guess you could visualize layers or something like that. So to generate the next state, first we need to declare a variable so that we can get the next state inside there always. And then we can loop through every single unit or space coordinate inside our new state. We need, this variable is unnecessary, sorry. So we need a variable to count the number of neighbors surrounding our number of active neighbors surrounding our given coordinates, and this neighbors help us determine how the state should change. So it determines whether our new cell should be active or inactive. So how we count that, this is kind of similar to what we did in a previous day where we did something about waiting in a seating area, something about that. But you can go watch the video. Maybe I'll include a link to that. So we look at all the dx, dy's. So we're just looking at all 26 possible cubes. We just need to consider every x and y coordinate that is within one of our current one. So we need to consider a change in x of -1, 0, or 1, change in y of -1, 0, or 1, change in z of -1, 0, or 1. And this gives us 27 possibilities. But also we need to make sure that the changes are not all 0, because if they're all 0, then we're just considering our current square, and we don't want to count that when we're counting our neighbors. So we also need to make sure that this is inside the grid, otherwise we're going to get an index out of range error. So we just make sure that x is within the range of possible x, y is within the range of possible y, and z is within the range of possible z for our neighbor cube. Okay, we also don't need this. This is unnecessary. But yeah, okay. If our neighbor square coordinate is it should be a cube actually. If it's a pound sign, then we add 1 to our neighbors. If it's not, then we add 0. This is just a shortened way to say it. This is a boolean. It gets cast to an integer, and that integer is kind of going to be 1 or 0. So we add that to our neighbors count. At the end of all this, after we're done considering all 26 surrounding cubes, we look at our current state. If the current cube is currently active and our neighbors is less than 2 or greater than 3, because we need it to be exactly 2 or 3 for it to stay active. If it's not either 2 or 3, then we just set it to be inactive. If it's inactive and it has exactly 3 neighbors, then we set it to be active. Otherwise, it just stays the same. So this is our basic function, returns the next state. Okay, after that, our n is basically how large this is. We're not exactly given that this thing is going to be n by like n. We're not given that this is going to be a square, but my input is a square. I'm going to assume your input's also a square. So we're just going to assume it's a square. And the side length of the square is going to be how many lines are in our input. So we also, again, as I said at the beginning, we're going to need a size to determine how many squares we need. I mean, like how big our slice of the infinite pocket dimension is going to be. And then, yeah, that's going to be 50. It's big enough. If you run it, it's going to run a little bit slowly, but it's going to run in under a minute, so that's fine. We also have this count active layer. Layer is going to be a two-dimensional grid. It counts the number of squares or cubes in that grid that are not inactive. Okay, after that, we get our input state, and then we put it in the middle of our 3-dimensional grid. So if you can imagine a cube, we put it in the middle, and then we put it in the middle slice. So we look at the middle slice, that's a 2-dimensional grid, and then we put our input into that 2-dimensional grid in the middle. And we want to put it in the middle just so that we have like enough space on the sides to buffer it out and to provide enough space for the operations. Okay, we don't actually need this, but you can see if we run it, it prints out the initial state, and this is just the middle layer that we're putting everything in initially. Okay, after that we just keep looping through the states. I just have this like log, I guess. After that we actually don't need that. This should not be indented. We don't have to calculate that every time. But that's basically it. That's basically it for part 1. I'm not going to go into like the details of every for loop and every variable declaration. That's just, I kind of already went over that. So hopefully that's enough. This is pretty frustrating to solve, so I'm not going to go through it again. All right, so let us go to part 2. Okay, part 2. For some reason, your simulated results don't match what the experimental energy source engineers expected. Apparently, the pocket dimension actually has 4 spatial dimensions, not 3. The pocket dimension contains an infinite 4-dimensional grid. At every integer 4-dimensional coordinate, there exists a single cube, really a hypercube, which is still either active or inactive. Each cube only ever considers its neighbors. Any of the 80 other cubes where any of the... Okay, so on. So there's 80 neighbors. The initial state of the pocket dimension still consists of a small flat region of cubes. Furthermore, the same rules for cycle updating still apply. During each cycle, consider the number of active neighbors of each cube. Okay. Simulating a few cycles of this from this initial state produces appalling configurations where the result of each cycle is shown layer by layer at each given z and w coordinate. Okay, so 4 dimensions is kind of hard to wrap your head around, but fortunately we don't actually need to visualize it. We just need to put it into our code. So I'll be back in 5 seconds. Amazing. Okay, we finished, and our answer is 1728, which suspiciously is equal to 12 cubed. So that's the right answer. Okay, that's weird. And our first answer was 215, which was 1 less than 6 cubed. But that's probably just a coincidence. Okay, let's explain how I solve part 2. So this is kind of similar to part 1. We just need to add an additional w coordinate. And as you saw, this runs much more slowly than part 1. So we have a z coordinate. We have a w coordinate, and this is the layer above a layer. So we're having a cube, and each cube is part of a 4-dimensional layer. So we just need to add our w coordinate, and this is a layer above a layer. And we need to make our grid 4-dimensional instead of 3-dimensional. So it has a 2-dimensional grid stacked on top of each other to make a cube, and then you do that multiple times. So multiple cubes, that's our 4-dimensional layer. We have, this shouldn't be indented. Okay, so we have these 4 possible changes in w, x, y, z now. 4 new coordinates for the neighbors, so there's going to be 80 here. We need to make sure make sure they're inside the coordinates, inside the grid, I mean. They can't be all 0, otherwise it's going to be the same, it's just going to be self. And then we just add on whether it's equal to $. And then over here, it's the same rules. Neighbors need to be 2 or 3 in order to stay alive, and neighbors need to be exactly 3 for cell to become alive if it's dead. Same thing over here. We just make it 4 layers instead of, sorry, 4 dimensions instead of 3 dimensions. We just need to set it to be in the middle cube and in the middle layer of that cube. So after that, we just run it 6 times, and we need to count how many, I guess, hypercubes in there are not equal to are not inactive. And I just did this with kind of more fun variables. We have cubes, and then we have layers in the cubes, and then we have rows in the layer, and then we have hypercubes in each row. After that, we're done. We just output the count. So that's pretty weird. That was pretty weird. That took a long time to run, but that's okay. It still ran in under a minute, so I'm happy about that. And that's pretty much it. Okay, I'm going to push the code to GitHub right now. All right, so now it's pushing to GitHub, and okay, it's done. You can check out this link in the description. It's going to have the GitHub repository. Okay, so that's pretty much it for day 17. Hopefully that made sense, and we're going to be arriving at our island shortly, hopefully. So we've taken a very convoluted route, and hopefully we'll be at our destination vacation island soon. And this series is coming close to an end, but we still have a few days left, so we'll see how that goes. And after that, there's always USACO. USACO is coming up this weekend. That's the USA Computing Olympiad. Let's just go there. So you can see, I don't know if there's an about page. There's an overview. Okay, this is the overview. So you can just read this. I'll put a link to USACO, I guess, in the description as well. But you can search it up. It's usaco.org. Pretty simple. All right, so that's pretty much it for day 17. If you liked it, please like the video and consider subscribing. Let's get to 400 by the end of the year. And please leave some feedback, whether it be in the comments, whether that be a like, or whether that be DMing me on Discord. My Discord is in the description, so feel free to reach out to me. And that's it for day 17. Hopefully that made sense. Hopefully that was helpful. And I will see you tomorrow with day 18. Goodbye.